Hey everyone, and welcome to this video about traffic analysis. If you have not already watched the previous video about traffic assignment, I encourage you to start with the traffic assignment video because we will reuse a lot of what we have learned. This video and its content is copyrighted by Bentley Systems, so please do not share it. In this video, we will first focus on validating the result of our assignment. Have we reached equilibrium, true equilibrium? Are the results making any sense? And then we will spend the last 3 sections around running specific analysis. So we will learn how to do analysis of paths, and then 2 examples to do distance analysis and select link analysis. So these ones are the most frequent analysis you will want to run. To make sure that our assignment models are representing some kind of ground truth, we need to have observations about the reality. So cities will run traffic count campaigns, and they will include these traffic count values either as a linked attribute or a turn attribute, depending on what was counted. And they are imported usually either as a CSV file or depending on what format you're storing your data, you have different formats you can import. For the demonstration database, for the Winnipeg database, traffic counts were imported in the extra attribute @obs, which is the shorthand for @observed. We will use the general worksheet to identify where these traffic counts are. So let's head back to our demonstration project. If you have not yet reopened it, I encourage you to do so and to open the general worksheet, which can be found in Worksheets and Tables under General Worksheet in the Project Explorer. From there, we can go to the link layers controls. We make sure that we show and display all the links. So the link layer filter is 1, and we show a bar value of 1 if there is a traffic count, and a value of 0 if there is no traffic count. So it's a logical operation. And we know that we have our traffic count stored in @observe. So we want to know when it is greater than 0. And by doing so, I have a map displaying for me a bandwidth of 1 wherever there are traffic count data available. We can note that there are a good coverage of traffic counts in the south shore of the city, but there is not many information on the north shore. So we might be missing some information, and it might be interesting to run a campaign to add extra counters and add extra information on this section in the city. Another way to identify all links with traffic counts would have been to use the network find. So I'm using network find, writing the expression @observe greater than 0. And then selecting, you can see that we have 70 links with a traffic count information. And you can select them and display them. Using the network find, it is also useful to run exploration. So we have traffic assignment results. I'm going to switch to scenario 3000. So we have traffic assignment results, and we would like to know whether we have more cars as a result of the model assignment than what we observed as the ground truth, or if we have fewer cars. So in the network find, I can investigate this information by doing @observe greater than volley_u, since volley_u is the traffic count results from the assignment. Well, it's not the traffic count, it's the traffic volumes from the assignment. So now we can identify 49 links where the traffic counts are higher than the assigned volumes. Does it mean that the demand is too low? Does it mean that the capacity is too low? Or is the traffic count not perfect? This is a matter for the analyst, for the modeler to investigate. Now, if we want to see the remaining counts where the observation is smaller than value, what we can write is at observe smaller than value. And here you can see that we are getting basically all of the links, because if at observe is 0, so if there is no traffic count, then it is below the modeled traffic volume. So I will add an additional condition using the end, so dot end dot keyword operator. You can also use the double %. So end at observe greater than 0. And with that with that combined filter, we find 21 links, which are underestimating, where we are overestimating volumes. Oops. Identify where they are. Quick reminder, if you don't remember what are the operators available to you when you write an expression, you can always go back to the window, intrinsic function, operator, and attribute lists to have a list of all operators that are available to you. So from this list, when I do right click from the network find list, if I do right click, I can identify them. But as you can see, they disappear pretty quickly. So if I want them to stay, I will click on the add to selection. Notice that I can also clear or remove from selection. And I have the option zoom to and center on. So let's go with add to selection. Now they appear in green and they will stay there for as long as I want. If I want to still have them selected but not appear, I would go in the network find menu and deactivate the show selection on map option. I can also go in the selected tab of the network find panel, and from there I can deactivate one by one. I can deselect if I want to, one by one the element, or clear the selection all at the same time. Here there is one thing that we notice right away, which is the places where we are overestimating seems to be spatially correlated. So there might be a common, there's a good chance that there is one or two source of issues that can be corrected. Okay, so we have seen that slide, we have seen that slide. For the next demonstration, we now want to compare the predicted volumes from the traffic assignment versus the observed volumes. To do that, we will use the table volumes and times on links, which we learned about in the previous video. So back to my project explorer, I'm going into worksheets and tables, generals, results, analysis, traffic, and we have volumes and times on links as a table. You can see here there's a small table icon. So open this one. It contains general statistics I might be interested in, as volume, distance traveled, vehicle hour travel, and we will add the information that we need. So the information we need for the comparison of predicted volumes versus observed volumes will be a first column with the at observe attribute. So if I want to add a new column, I can do a right click on the header of the column. I want to add the new column 2. So add a new column to the right of this one. And I will select the attribute at observe from the drop-down menu. And click on OK. Note that here I'm adding the attribute @observe, but in your project, the traffic counts might be stored in a different table, in a different extra attribute. So you will pick the one that corresponds to your project. Once we have added the @observed column, this is what we just did, we want to add a new column as well, which contains the relative difference between the observed and the predicted volumes. So it can be relative to the observation or relative to the predicted volume. It makes more sense to do it relative to the observed volume because this is our ground truth. So I invite you to add a new table and name it relative difference and give it a good description, relative difference between predicted and observed volumes, and set the number of decimals to 2. We will also include the minimum and the maximum as well as the average. Back to the desktop here, doing a right click on Add Observe Column Header, adding a new column to the right of this one. The expression will be value minus @observe divided by @observe. The first note here, the total traffic, if you followed the previous video, the total traffic might actually be vol.au plus vol.ad, right? So the background traffic is usually also counted by traffic counters. The name will be rel.diff, relative difference, and the description will be relative difference. Difference between predicted and observed volumes. The number of decimals will be 2, and we will include summary, maximum, and average statistics. We'll then click OK. And here, first of all, we have the new column with the header we decided. If I let my mouse over the top of the header, it shows me the description of the column. We see we have plenty of infinity value because we divided by the attribute @observe, which value is 0 for many links. So we have a lot of infinity values. So we want to filter this table to not include links where there is no traffic counts information. So we will set the filter to @observe greater strictly than 0. And with that, we filtered only the 70 links where there are observed traffic counts, and there is no division by 0 anymore. So we are able to find the minimum, the maximum, and the average. Once we have done all of this preparation work, we can save this table, and we will be able to come back to it later if we are doing modifications to the network or to the demand to see how it impacts the measure of our performance in a way, so the relative difference between the observed and the predicted traffic counts. It is also important to note, the screenshot is actually very good for that here, that sometimes the relative difference might be major, might be important. So here the forecasted volumes are 17 times bigger than the observed volumes. But it does not necessarily mean that our model is bad, because as you can see, the observation here is 10. And it's not very likely that the city will spend money for a traffic counts on a road where they know that there is nobody coming through. So this 10 is a bit suspicious. It could be that it was a day where there was construction on the road, so nobody went through. It could be that it was the wrong date or a major weather impact, but it's not because you have observation data that you should trust it blindly. Always try to find where the discrepancy between observation and model comes from. It can be the model, or it can be the observation if they were not cleaned good enough, or if there is a specific issue with the day of collection, for example. So let's go and save this table. click on Save As. We give it a name. The name will be traffic volume, predicted, and observed. And we change the file name as well. The file name will be, actually we will save inside our worksheet subdirectory and our training subdirectory, and we will name it traffic volume, predicted, and observed. And we can click on OK. And now every time we go in the training directory of our worksheets and tables and reopen this new worksheet, traffic volumes predicted and observed, every time we will see the view of the data as it is now, meaning that it will all of the content of the table will be updated with the latest and freshest data of the model. For this next demonstration, we will compare still the observed traffic counts to the model traffic counts, but this time using a link scatter plot to better visualize how good our fit is in a way. So to do that, we will use the link scatter plot worksheet. Back in the desktop, you will find it under worksheets and tables, charts, XY charts, link scatter plots. Here you can see that there are the green selections of my links that are showing. So either I can clear my selection by going in the network find under the selected tab, right click, clear selection, or I can hide away the selection on map. So myself, I will keep the selection on map and I will clear my selection. So back here, we will open the link scatter plot layer controls. And we need to decide what goes on the x-axis versus what goes on the right axis. So on the x-axis, usually you will set your ground truth, or I like to set my ground truth. And in our case, the ground truth is the observed volume. On the y-axis, on the y value box here, you need to set your modeled values. And in our case, this is volley U. So we see a scatter plot where each point represents a link. So if you let your mouse over the link, you will have a tooltip with the link identifier. The first value is the X value, so the @observe, and the Y value is the Y, and the second value is the Y value, so the Y-axis, the modeled volumes. We also see that we have plenty of dots on the y-axis associated with the value x equals 0. This is because we don't have traffic counts for every link. So we need to apply a filter for the links that are not relevant for our analysis. And the filter is, as always, @observe greater than 0 strictly. And now we have automatically scaled a graph that looks better. If I want to manually scale it, I can change the value from here and lock my scales, if that makes sense. Next, we will want to compute the regression of this model. So we will go in the regression layer controls. Here and activate compute and check the box compute linear regression. It will remind you of the number of data points, 70. Here you have the option to display one confidence interval or more than one. Then you have the interception at origin, so the A part of the regression, of the linear regression. Then the B is the slope. So if we had a perfect model, we would have everything aligned on the line y equal x. So A would be equal to 0 and B would be equal to 1. Then we have the root mean squared error, and the R2. We will navigate to the title, descriptions, and symbol layer controls, expand it. And here we have the title. Currently, the title says link scatterplot. And you can see that we are using a string substitution. Right now, we are substituting from here. So if I change the title to predicted versus observed volumes, we see it changing from there, or I could have written it directly here. But if I go and display the list of predefined expressions, you can see that we have other options which will include, for example, the regression values. And this is interesting. So let's select this option. So first we show the caption, then we have a new line, then we show the regression values. So now the regression values are available from here. If I generate an image out of this graph, it will include these statistics as well directly from here. From the title, description, and symbol layer controls, we can also play with the symbols that we want to show. So circles are great if you want something that's maybe more an indication of like a cross. So the plus sign is a cross, easier to see. And you can play with the size and the text angle of the labels of the scatterplots. Once we have styled our scatterplot the way we want to, we will save it, and we will save it directly under the training subdirectory, and I will leave the title, the name, predicted versus observed volume. In the next demonstration, we will generate an histogram which represents the distribution of travel time for the auto mode. It is an important point when we are validating that our models is giving useful results, because we know that in the market of transportation, in the market of mobility, some modes are not really competing with each other depending on the distance of transport. So for instance, the pedestrian mode is not a real competition to the car mode for long distance trips. If there is 10 kilometers, if there's 20 kilometers, it's unlikely that anyone chooses to walk. Whereas the subway and the car mode might be more in competition. So if we want to represent faithfully the base reference, the base year, we need to be able to be sure that we represent these phenomena correctly. So I invite you to open the histogram. So we have several types of histogram worksheets. So we are going to open the one for the matrices. Okay, we have seen that we played with scatter plots for the links before. We didn't take time to highlight the fact that there is a scatter plot for every network domains and even for the matrices. Well, for the histograms, it's the same. So we have histograms for transit lines, links, matrices, etc. We will go for matrices. To represent the trip distance distribution, the travel time distribution, we will use the x value for the binning, and we will use travel time for the binning. So on the x-axis. On the y-axis, for the frequency of our distribution, we will use the demand matrix. We will also apply a filter, and because we want to include all of the matrix values, either it will be 1, so in our case it will be 1, but we could apply another matrix to include or exclude some odd pairs. For instance, if we are not interested in external zones. Let's move and configure our matrix histogram here. The X value will be MF4, so the auto time for the base scenario, for the reference scenario. And the Y value will be the demand, so MF1, the auto demand for the base scenario. This is giving us a first histogram where we have the travel time in minutes, so 0 to 10, 20, 30, 40 minutes, and the frequency here in number of trips as seen from the demand matrix. Here we are including all of the matrix ODPR values, but we can apply filter, and we see at the top that we have the option to show the distribution as a cumulative distribution. So if I check that, we see that it goes a little bit off the chart. So I will use the automatic adjustment to readjust the Y range. So cumulative distribution means that we go up to 100%, right? So we go up to the total number of trips. We can check the box relative distribution. So this time it is all put in on the common denominator. So it will go up to 1, so 100%. And if we want to show numeric values for each of the bar, we can check the box numeric values. I will remove the cumulative distribution and the relative distribution and recompute my Y range. Okay. So here for each of the bar, we are seeing the related number of trips. Okay. So here we have 0 to 2 kilometers, 0 to 2 minutes, there is 1,000 trips. 0 to 10 to 12 minutes, we have 500 trips. If we want to change the binning here, we can play with the X range. So for example, we could go from 0 to 45 by jumps of 5. Okay, so 0, 45, 5. Okay, so the first value is where we start, the second value is where we end, and the third value is the size of the bin. We will want to automatically recompute the Y range and lock these ranges so that they can come back to it later and it hasn't changed. So here we see a quite typical trip distribution, travel time distribution, where there are not so many travel tips which are very small, and then we have a longer tail for longer travel times trips. We can also include some statistics on our graph to show the average and the standard deviation, and they will be shown as the average will be shown as a triangle, and the standard deviation as the brackets that you see. So this is one standard deviation around the average. To do that, we'll go to the statistics layer controls, check the box show average, check the box show standard deviation, and you can see them at the bottom. They are kind of small, so if you want to see them more accurately, you can always use the magnifier tool. And the magnifier tool will allow us to have a more accurate reading of the value. We have already seen that there are several tables available to show most commonly used, to show and analyze most commonly used performance measures, such as the vehicle distance traveled, whether it is in VKT, so in kilometers, or VMT in miles, to show the vehicle hours traveled, VHT, and the average speed. This information is available as a table for all of the links, or we also have special tables to show summary information by category. So when you look at the project explorer under general results analysis traffic, there's a subcategory summaries, which lets you run aggregation by link type, terminative function, turning angle, and volume delay function. This will be useful, for instance, if you are interested in knowing the performance measures for the highway versus the the highway versus the local roads, or the left movement versus the right turning movement. In addition to these summaries, for each table, we also have a filter that allow us to retain some links or turning movements for our analysis and discard the rest. In the demonstration database, we have an extra attribute, a link extra attribute called @dist, and it contains the district number to which the link belongs. So it's a useful attribute because it now allows us to use the traffic volumes and times worksheet to display the performance measures by district. Okay, so the vehicle distance traveled and vehicle hours traveled, as well as the speed and the average speed. Let's apply this demonstration. We go to the desktop and find the results, the volumes and times on links worksheet. So the last one in the category. It is initialized with a filter, so road network no connectors, and we will apply an additional filter, so and. You can write n%, n%, or you can write dot and dot. It's the same operator, same logical operator. So n at dist equal 1. So this is for district 1, and I can easily navigate through the districts and report on them one by one if needed. We often need to compare results between scenarios. It can be because we are doing forecasting and we want to compare two scenarios, one with a bridge, one with a tramway, or whatever we are interested into. Or it can also be used, the scenario comparison can also be used to make sure that we have reached convergence and that we have reached a user equilibrium for our traffic assignment. So we have, for instance, we have link results and the associated data that we want to compare, and we can compare it in a table by having the data side by side, on a map by plotting the differences between two scenarios, or on the scatter plot. We also have matrix results, so the OD travel times. And to compare travel times between two scenarios, we will use a matrix table, a matrix scatter plot, or an histogram comparison. If you look in the general category for worksheets and tables, under results analysis scenario comparison, there is a bunch of worksheets that are already available and ready to be used. In this demonstration, we will learn to use the compare traffic volumes, volume and times worksheet to compare two scenarios. So in our case, this will be scenario 2000 and scenario 1000. So I invite you to open the worksheet, compare volumes and times. It will be under general, results analysis, scenario comparison, compare traffic volumes and times, the one with a map icon. So double click on it and open it. When it opens, right now we are seeing no comparison at all. Well, this is because currently there is only one active scenario. It is scenario 3000. But what I wanted to do was to compare the scenario 2000. The scenario 2000 contains an assumption that we built a new bridge. And we wanted to compare this scenario with the scenario 1000, which is the reference condition. So today, what's happening today. So I invite you to make scenario 2000 the primary scenario by right-clicking on it and selecting a replace primary scenario. So now we have the active scenario being scenario 2000. We also need to open the scenario 1000 because currently the data is not loaded. We cannot do any comparison. So do a right-click on scenario 1000 and select the option open. You will now have two scenarios in the list of active scenarios, so 2000 and 1000. You can reorder them if you want to and make the scenario 1000 the primary one. But we wanted, so by drag and dropping, I'm reordering the scenarios. if we take a look at the map, and I'll take the time to include a web-based map from the media online map layers. There it is. Double click on the straight one so that we have some context information. Okay. So we are seeing here that there is a new bridge, the Kilden Bridge, that was built on top of the river here. The legend lets us know that some links are displayed in white if they exist in both scenarios, in green is if they exist only in the scenario 2000, and in yellow if they exist only in the scenario 1000. Then we have a bandwidth plot showing the difference between the two scenarios in auto volume. So looking at the link layer, link comparison scenario 2000 minus 1000, expand the controls. Currently, we are looking at the difference of VolleyU from scenario 2000 minus VolleyU from scenario 1000. So if this value is greater than 0, it means that there is more volume in the scenario 2000. For example, the bridge only exists in scenario 2000. So indeed, there are more cars on the road in the bridge in the scenario 2000 compared to the base reference scenario where there is no bridge. So VolleyU of scenario 2000 minus VolleyU of scenario 1000. And the color is an indication on whether it's greater than 0 or smaller than 0. We also have the legend here letting us know an estimate of how much traffic there is, how much the difference is between the traffic. And we can see that when there is no bridge, the traffic that wants to cross the river has to make a big detour and basically find the nearest bridge to reach their destination. We are currently showing the actual difference, but we could also be interested in relative difference to the larger value or to the current scenario or to the other scenario. So we will look at the difference with the other scenario. The other scenario is the second one, so the difference with the base scenario. Oof, that's a bit big. I will have to play with my scale to get to something that makes more sense. Okay. We also have a way to work with the maximum relative difference. Here it is capped to 1000 because we are dividing by 0. So maybe it's not the best option to do in percentage relative to the other scenario. So if we go in percentage relative to the larger value, we have something that goes between 0 and 100. And that's easier to actually find the differences between, like the big differences between scenarios. We also have a threshold. If we are interested in only showing the biggest differences, we can set the threshold to the lower value and the higher value separated by a comma. So if I set 20, minus 20, that means I only include the very large differences. Whereas if I do the opposite, minus 20 to 20, that means I include only the small differences. And I will change back to actual to see that we only have volume differences ranging from 0 to 20. Okay. Now we also have at the bottom of the map a table that contains the value from, so VolleyU from the scenario, the first scenario. So traffic 1 here is the volume in scenario 2000, and traffic 2 here is the volume in scenario 1000. We have the actual difference, the relative difference. We have the same for background traffic, and we have several statistics at the bottom, minimum and maximum, to help us find where there are the biggest differences. We also have the speed differences at the end of the table on the right. For this demonstration, we will compare the traffic volume resulting from two different scenarios as a scatter plot. So I invite you to open the worksheet XY chart links, which you can find from the Project Explorer under Worksheets and Tables, General, Results Analysis, Scenario Comparison, XY links, XY chart links. By default, it is already pre-configured to show us the comparison between value. We can change this value either from one of the predefined expressions or write our own expression, and it will be evaluated against the two scenarios, and the corresponding point will be displayed. So here what we can compare, if we let our mouse on top of one of the dots, it will tell us which link it is, what is the value in the primary scenario, and what is the value in the other scenario. So here I took kind of an extreme link, so one of the bridge links which were added, and we can see that there was a value of 0 in the reference scenario, and then it is heavily used. There's 1,000 cars on top of it in the AM peak. We have a legend letting us know that if the value is the same in both scenarios, so if the traffic volume is the same, if the auto volume is the same in both scenarios, the dot will be represented in gray. If there are more traffic in scenario 2000, so in the primary scenario, then it will be in red. If there are fewer, it will be in green. Having a scatter plot is interesting, especially with the tooltip functionality, as it allows us to pinpoint outliers and try to understand why is this link benefiting or resulting in more traffic. Let's change here our expression for the x value. Notice how currently the y value shows PCE and then an arrow to the right, VOLEU. So PCE is the shorthand for pointer to the corresponding element. So if we take the VOLEU for a specific link, we will take the VOLEU for the corresponding link on the next scenario opened. So here I will change this for the total volume, so VOLEU plus VOLED. And you can see that automatically the Y value has been updated to show me VOLEU plus VOLED from the corresponding next scenario. Similarly, the style has also been updated to correspond to the expression I've set in X value. In this next demonstration, we are comparing the travel time distribution between two scenarios. So we have results for the scenario, the base scenario without the bridge, and we have results for the scenario with the bridge. So that's two histograms that we want to show. When we compare histograms, when we compare matrix values, it works a bit differently than when we compare network. Because to compare network, we need to open two scenarios. Matrices are all stored in the emBank. There is no storing by scenarios. So we don't necessarily have to open multiple scenarios. We can just work with the comparison of matrix histogram worksheets and directly display the two histograms. So I invite you to open this worksheet. You will find it in General, Results Analysis, Scenario Comparison, Comparison of Matrix Histograms. Expand the layer controls compare matrix, and here you have two sections, two subsections, one for the first distribution, for the first histogram, and the second section for the second distribution. The data matrix 1 will be the information we use to compute the bins. So the The travel time for the base scenario is stored in MF4 for this project, and the total demand is stored in MF1, so we are weighting our distribution by MF1. We don't apply filter, we take all of the OD pairs. Here we see that the legend is currently showing MF4 times MF1. If we want to show something different that we type, we could go with travel time distribution. Well, I guess maybe just base scenario is enough. There we are. Then for the second distribution, the travel time for the scenario with the bridge is stored in MF6. So we're going to use MF6. And for the weight distribution, well, this is the same demand, so it's MF1. And they are just using different networks to arrive to that destination. The legend will be Kildonan Bridge scenario. There we are. And next, we need to click on the box auto axis so that it computes the bins for us. And there we are. If we prefer to customize the bins and the settings of the diagram, we can go in diagram settings, set the X range. So for us, it will be 0, 45, 5, and set the Y range as well. We're going to do 0 to 16,000. Maybe a small typo here, 0 to 16,000. There we are. Then you can also see that we have the same boxes as before, so we can show the distributions as cumulative or relative. We will leave it as it is now. What we want to compare is the distribution for the base scenario versus the distribution for the Kildonan bridge scenario. And basically, there are a lot of places where the distributions overlap, but we notice here that there are more people in blue, so in the base scenario. So for the longer distance, there are more people with longer distance trip. And for the shorter bins, so for these bins, it's green, it's not blue. So this is there are more people within shorter bins when we built the Kildonan bridge. So basically, we have shifted the distribution from longer distances to slightly smaller distances. At the bottom, we also see the average and the standard deviation. Always use the magnifier tool if it's too small. And we can see that the average has shifted a little. Same thing for the standard deviation, but very little changes overall. Comparing scenarios and comparing matrices is useful, especially to make sure that the assignment has converged. We need to do it. We need to be sure that we have reached the user equilibrium because it is essential to be able to perform meaningful analysis. Only when we know that we have reached the user equilibrium will we be able to do fine solutions analysis, compare scenarios, carry out economic evaluations. Plus, nowadays we have a new generation of computers. Well, nowadays it's been a while now that we have very powerful computers, and we can reach the user equilibrium. It's a possibility, and that's so we shouldn't settle for anything less than user equilibrium. So in order to see how to use this comparison functionalities to ensure that we have reached user equilibrium, what we will do is we are going to run a Solar traffic assignment. Then we are going to make a copy of this scenario, and we are going to continue the Solar traffic assignment for more iterations. And then we will have two scenarios holding results from different stopping criteria, and we will be able to compare. So if we were at user equilibrium, there shouldn't be any meaningful differences between the stopping criteria where we stop at 200 iterations versus 300 iterations. If we stopped, if we reach user equilibrium, it should be the same results. So let's do this. Let's move to our desktop, open the modeler with the modeler button here, and we will start by making a fresh copy of scenario 3000. So I invite you to find the modeler tool, copy scenario. I'm using the search box, finding copy scenario, opening it, making a copy of scenario 3000, copying to scenario 3000, and I think we are at 7. So this will be named first traffic stopping traffic assignment criteria. We will click on override scenario, set the new scenario as the primary scenario, and run the tool. So now we are going to run a SOLA traffic assignment. So find the tool SOLA traffic assignment from the EMME standard toolbox and the traffic assignment, SOLA traffic assignment. We already learned last video how to configure this tool. So instead we will load an existing specification file. So click on open and find the SOLA traffic assignment.ems specification, which is here. Click on open. So we are using background traffic with transit vehicles. We are using MF1. No analysis. The stopping criteria is 1,000 iterations. We will change that. And set up a maximum number of iterations of 170. A relative gap of, what can we use? 0, I guess. A best relative gap of 0.01 and a normalized gap of 0.005. So we are making like a first attempt at finding the convergence, finding the user equilibrium. We are using a maximum number of processors and RAM. After the assignment is completed, it's a good thing to look at the logbook and make sure that we understand what happened. So we stopped on the normalized gap after reaching a value of 0.006. And if I take a look at the convergence charts, we had around 100, like 90 something iterations. Okay. So when we look at this convergence chart, it's looking like we have almost reached a point where the gap measures is stable. But to be sure, we need to continue this assignment, and we need to look at the results as well. So let's make a new copy. So we go back to the copy scenario tool. This time we copy the scenario 3007, which is the one we've just run against. We are going to copy it on scenario 3008. The new scenario title will be second traffic assignment criteria. We will preserve the scenario status across the copy. So it will transfer the information for the assignment, and that will allow us to use the tool continue traffic assignment. So we have made a fresh copy of scenario 3007, and back in the EMME standard toolbox under traffic assignment, we have a tool named continue traffic assignment. So open this one, and you can see that automatically it was reloaded with the values of the stopping criteria of our precedent run. Okay. We also have a summary of what was run precedently, as well as how did we stop. So we stopped at 95 iterations on the normalized gap. So if we want to go further in in the assignments, we will have to relax a little bit the constraint here. So to relax the constraint, because it's stopped on the normalized gap, I will set the normalized gap either to a smaller value or completely to 0. 0 here as well. Actually, I'm going to leave that one to 0.01. Maybe not the relative gap. The relative gap will remain 0. The best relative gap will remain 0. The relative gap will be 0.001, which is a fairly common value, 10 to the minus 4. And when we are ready, we click on the run button. So what's great with this continued traffic assignment tool is that it does not rerun the first 95 iterations. It starts from the results of the 95 iterations and do it again. So this time it ran through. We can click on view in the logbook. And so yeah, so it's great because we don't have to rerun the first iterations. We are gaining time. Here with this demonstration project, it's very fast. It's almost as if we did not gain time. But now imagine that you have 100 classes, you have 1,000 analyses, and you would like to know whether or not you have reached your equilibrium. Maybe the assignment takes 10 minutes. So going a few iterations more, just for the peace of mind, you will be able to compare 1,000 iterations with 1,010 iterations. And if you see that the user equilibrium is reached, then this is great. So gain of time. The convergence chart. Let's see what it is. Okay. So as before, with this time, instead of starting from 0, it starts from 95, right? We have already done the first 95 iterations. And so the convergence is kind of reaches lower values much quicker. My apologies about that. And we can follow what's happening here. So let's put in practice what we have just learned about to compare the results onto the two different networks and see if we have reached user equilibrium. I'll go back to the desktop and save and reload and refresh my data. We will use the compare traffic volumes and times worksheet to compare the scenario 3007 and scenario 3008. And if we are seeing major differences, like in this example here, we are seeing differences up to 50 cars on a link, 50 cars per hour. This is not user equilibrium. We have not reached user equilibrium because if I run more iterations, I see major enough changes in volumes on the links. So finding the appropriate worksheet, compare traffic volumes and time, not on the table, traffic volumes and times on a map. Always adding a little bit of context with the online map layer. Just double clicking on it makes things more beautiful. And for our practice here, we are seeing differences. Let's open up the right scenarios. Right now it's scenario 1000, which I close, and scenario 3007, which I open. So right now, between scenario 3007 and 3008, we are seeing differences almost up to 15 cars per hour on links. So that means we have not yet reached convergence. We need to go deeper in a sense. So let's move back to our modeler. And let's reiterate our operation. So if I copy the scenario 3008 to 3009. And this time this will be third traffic assignment criteria that I test. I can use the continue traffic assignment once more, relax a little bit the maximum number of iterations. On our second criteria, we had a relative gap of 0.0001. We are going to go one level deeper, so 10 to the minus 5, and run the continue traffic assignment tool. From then on, we can go back to the desktop, refresh the desktop, make sure that we are comparing the appropriate scenarios. So 3001 and 9 to 3008. So I'm opening 3008 and closing 3007. And so now you can see that we went from differences that were between 0 and 15 to differences that are between 0 and 10. So I can continue this work and tighten up my convergence criteria and reiterate this loop until I'm sure that I have reached some convergence, meaning that the difference between the two scenarios, so basically the scenario with a certain specific criteria and the scenario with one iteration more or two iteration more, does not give me major differences. So differences that are bigger than one could be considered major differences. At this point, we have reached the first checkpoint where we invite you to open up the practice booklet that was joined with the training content. And we will learn about analyzing traffic assignment results. So I invite you to put the video on hold, on pause, go to the practice booklet, do the practices, and then continue the video to see the correction and to see the remaining of the course. In this practice, analyzing traffic assignment results, there are there are 3 sections. In the first section, we are using a table to look at the results of the traffic assignment and to look at the volume over capacity ratio. In the second section, we will try to find links with potential problems. So links where the assignment result is different from the observed volumes. And eventually, we will use the link histogram worksheet to display different various link distributions. So we will start from a copy of what we've done in the last practice. So we have, I think it was practice. Let me see if I have it here. Practice 3 should be. So I invite you to make the practice 3 the primary practice, the primary scenario. And here we're just going to close the scenario 3003. In the modeler, I invite you to make a fresh copy of the scenario 3004, so the scenario from previous practice. In our case, this will be practice 3, which we make a copy to scenario 3010, and this will be practice 4. Click on the Run button, set it as the new primary scenario. And from here, we will open up the worksheet, volumes and times on links. Well, the table, volumes and times on links. So you go in worksheets and tables, general, results analysis, traffic, volumes and times on links. We don't want to see the connectors according to the booklets, and currently we are seeing only the road network without connectors, so that's what I want. Nothing to change. And we are being asked to add a new column which contains the volume over capacity ratio. So I will add it to the right of total volume, do a right click on the header, add new column to the right of this one. The expression will be total volume, vol U plus vol AD divided by at la cap, lane capacity, multiplied by the number of lanes. The name will be VCR for volume capacity ratio. The number of decimals will be 2. And I would like minimum and maximum. And average, why not? We now have our new column with the minimum, the maximum, and the average. We can sort this table by increasing or decreasing VCR by clicking on the header. So by decreasing order, we have the highest volume over capacity ratio, which is at 2. So more than twice the capacity is a lot of congestion. And actually, we will interest ourselves only for the link in the links which are over capacity. So we will add a condition to our filter using the AND operator. So dot and dot. And so we want and the VCR is greater than 1. So here I can either type again the wall expression or use the configurable attribute which we defined in one of the previous videos. Here I will type again the full expression. Lane capacity times number of lanes. And we want it to be over greater than 1. So every link which are above capacity. And we now see that VCR minimum value is 1 because we have just filtered everything that wasn't 1. From here, we will save this table. We will name it over capacity links and give it a name. We will save it under training. Over capacity links is the name of the table. And click on save. And this is the first section of our practice. On the second section, we want to highlight the links with potential problem. So we will open the worksheet volumes on links and turns, which we can find volumes on links and turns here with the map icon. And we will add a constant bar for the links which have traffic counts. So we open the layer controls for links. The bar value should be 1 only for links with traffic counts. So we can use a Boolean expression which yields a value of 0 or 1, depending on whether there is a traffic count or not. And the Boolean value will be at observe greater than 0, strictly greater than 0. So this results in 0 or 1. We now see all of the links with a bandwidth of the links where we have observed traffic counts. We also want to color the bars in order to identify overestimations and underestimations. So I will click on the link for the, I will click on the style for the bars. The expression will be at observe is greater than vol U. And if that's true, that means that we are underestimating. If that's false, it means that we are overestimating. So I'm going to put the label, the corresponding label. So green will be underestimating. Red will be overestimating. I will apply my filter here. It's not too bad. And click on OK. I notice I forgot to add a media-based map. So streets, for example, is a great way to add context to my maps. And since I put in the effort to have labels, I would like to have the corresponding legend. So I can click on Insert Legend, link bar, do a right click on the legend, go in the properties, hide the expression, just set a text size of 16 pixels, and there we are. Now back to our previous table with overcapacity link. So we have the volume overcapacity ratio. Let's add a new column with the observed traffic counts. So the expression will be at observed. The name will be observed traffic count, observed counts, and we're good. Or maybe the number of decimals should be no greater than 0. And click on OK. We would like to find the link with the largest overestimation. So the link where the difference between the observed count and the assigned total volume is the biggest. And so to do that, I will add again a new column, and this new column will be the difference between the two. So overestimations would be volley U plus volley D minus at observe, and here would be the name will be difference model minus observe. There we are. So observe difference model versus observe. If I click on the header, I can find the highest value. So we have a value of 3,620. So that's the, I forgot something. Here I did not filter for the links with observed values. So I need to add a filter here. I need to replace this filter actually. So and at observe greater than 0. Great. So now we have identified the link. So this is the link where the result is a lot bigger than the observation, 1,300. And we would like to see where it is on the map. So I can do a right click. I can zoom. Okay, zoom to selected item here, and then when I go back on the map, it will be centered. The camera will be centered and zoomed on the link selected. I could also mark or select this item, but I will go with zoom. And this is the from 423 to 450. Okay, zoom to selected. There we are. Just to make sure that we are at the right link, I will turn on the node number. Okay, 423 to 415. So here, this is a place where we are overestimating by a lot. It could be because we have made a mistake in the way we have configured our model. It could be because there is too much demand, but this is up to the modeler to investigate. Here we just highlighted where there are differences. And last question, we want to check the links for poor level of service measures. So to do that, I will go back to links. I will change the bar value to volley U. And I will change the bar style. I can load an existing bar style by clicking on the load button for links. And you can see that we have two bar styles already, one for highway level of service using the HCM 2010, and one for the urban street level of service, which is the one I will take. And we have the expression here, travel speed divided by the free flow speed. And click on OK. So with that, let's hide away the node boxes. It's a bit too much. With that, we are able to identify that there is very nice level of service everywhere in the city. Maybe because I forgot to apply the style breaks. So let's use breaks. Let's compute breaks. There we are. Obviously here I would prefer to not compute the breaks automatically and enter them myself manually depending on whatever is my classification of level of service. But for this demonstration, we will go with the automatically computed breaks. So one is when the speed assigned at the end of the assignment is the same as the free flow speed. And the lower level of service is when the speed is actually very low compared to the free flow speed. So here it's 10% of the free flow speed. And we are able to identify axes where there is congestion. Well, the level of service is not great. So everything that's red or pink is not so great. And last section of our practice consists in drawing link distributions. So we will open the link histogram worksheet, which we can find from charts, histogram, links. We'll go in the link histogram scatterplots where we are asked to not include the connectors in the histogram. So I will set a filter, not is connector. Either I type it myself or I use one of the predefined expressions. Then there's a first distribution we would like to show, where the X value is the facility type. So what's the distribution of highways, local roads, etc. We keep the value to y to 1, and we recompute the y range. So facility type by facility type, we are seeing here how many links we have of each type. We could actually still group by facility type, but this time, instead of just counting them, we see what is the vehicle hours by facility type. So to get the vehicle hours, we need the traffic volumes, VOLU, multiplied by the travel time through each link. So the travel time through each link is the time AU. This one is in minutes, so we need to divide it by 60 to get it in hour. And this way, we see that facility type number 6 has the highest number of vehicle hours traveled on top of that. And let's make a last distribution. This time the X value, the bins will be given by the speed, and the Y value will be just 1. So that gives us a distribution of speeds here going from 0 to 110 kilometers by increment of 10. And we have a big lump around 50 kilometers an hour, which is to be expected for local roads. We have a lump here around 90 kilometers an hour for, I guess, highways. And then we have all of the others, which are places with degraded performances, so low level of service. All right, so this is the end for our practices. I hope you had good results, and we will continue with our training. In the next section, we will learn how we analyze specific paths after an assignment was run. After an assignment was run, we always have some basic results available. The traffic volumes on links and on turns, P volley and volley. These volumes are the sum of the volumes for every class of the assignment. We also have the additional volumes, volley D, on links. So on links it's volley D, and on turns, P volley D. And we have the auto travel time through the links, time AU, and through the turning movements, P time AU. Note that the time, so time AU and P time AU, are based on the total volume for all classes. So it's based on volley U. and it should be consistent with the travel time matrix when the assignment is near the equilibrium. We also have class-specific results option. So that's an option that we can use to have volumes on links and turns by class, travel times, a matrix of travel times for each class. And we have seen that we could generate up to 1,000 analyses by class to get selected volumes on links and turns and OD values. So we will learn more about this part today. We use the path analysis with Sola to do a lot of different types of analysis. For example, to extract distance matrices along traveled paths for each OD pair, or to extract the total cost or the toll along each OD pairs. To run a select link analysis, where we want to know who is using a specific facility, or to do a partial assignment, aka a demand analysis. So to answer questions like, where would people go if we close a facility? What would be their diversion paths? Cold starts analysis will be, it's the cutoff analysis, where we retain the first or last few kilometers of a path. For instance, it allows us to study cold start emission models, or to study people looking for parking space at the end of their trips. The traversal analysis is used to extract gate-to-gate or sub-area demand matrices. The principle behind this analysis stands for the standard traffic assignment, the Solar traffic assignment, the path-based traffic assignment, well, for all assignments, traffic assignments which allow for analysis. But before you run an assignment, a reminder, please make sure that your assignments are converged, meaning that there is a user equilibrium, that you know that there is a user equilibrium. Otherwise, you will get results from your analysis, but they will just mean nothing reliable. To analyze a path, we compute a path attribute by combining the link attribute values, the turn attribute values along the path, and by using a combination, a path operator. So the plus, the summation, the maximum, the minimum. So for instance, if we want to compute the path distance, we would set the link attribute to length. We wouldn't have any turn attribute, and we would use the path operator summation. Here we have an example of a path with the first link 2.7 kilometers, a second link 6 kilometers, 5.1 kilometers for the third link, and 3.2 for the fourth link. So if you combine them along the path using the plus operator, the result, the path attribute values, is 17 kilometers. Now we need to go one. We use the path attribute value to select which paths will be included in the analysis. Paths are selected if the path attribute value satisfies the specified threshold. For instance, if we want to select paths which are longer than 10 kilometers, we would set a threshold from 10 kilometers to infinity, to 10,000 kilometers. And in the example below, we have three paths. One, if we combine the distance, so the link attribute is still the length, the operator is still the summation. So the first path attribute value is 17 kilometers. The second path attribute value is 9.8 kilometers. And the last one is 15.6. So with a threshold of 10 to 10,000 kilometers, we would have selected the first and the last path, and we would not have included the path in the middle, the second one. For each OD pair, origin-destination pairs, at the end of an assignment which is at equilibrium, it is highly likely that you will have more than one path. So if we want to compute one value for each OD pair, we will need to aggregate the path attribute values which allows the travelers to go from origin to the origin to the destination. So we have a set of rules to do this aggregation. First one is to determine whether we want to consider all paths for the OD pair or only the one who matches the selection. Then we may decide to apply the path proportions, meaning how many percentage of the demand is using path 1, 2, 3, 4. We can multiply by the analyzed demand or by the path value. So for instance, if at user equilibrium, we have the same 3 paths as before, but now we know that there is a proportion of 0.36, so 36% of the demand is using path 1, 46% of the demand is using path 2, and 18% of the demand is using path 3. We have assigned a demand of 100 people, or 100 trips. It could be 1,000, it could be 200. So let's see how the OD aggregation works for all of the different combinations available. Considering the aggregation rules that we have 4 types of analysis possible. The first type is the path analysis, where we consider all paths for each OD pair that are selected, and we multiply the path value by the proportion. So it's P1 multiplied by V1 plus P2 by V2. So path 1, path 2, path 3. And if we continue with the values from our example, 0.46 times 17 kilometers plus 0.46 times 9.8 kilometers, etc., etc. And we end up with an average of 13 kilometers, 0.4. We did not consider the selection, and it gives us the proportion weighted average value of the path values for all the paths used in the master assignment. For example, when we want to compute the average distance for all the paths used. The next analysis, selected path, considers only the selected paths and multiply the path proportion by the path value. So in our example, path number 2 was not selected, so we would have P1 multiplied by V1 plus P2 multiplied by V3 plus P3 multiplied by P3 by V3. And the result is 8.9. And so it gives the sum for selected path of the path value multiplied by the path proportion. And it is not used very often because there is no actual meaning about this information. But we can use it in matrix calculation, for instance, to obtain the average distance on path greater than 10 kilometers. So we would have to take this result and divide it by the sum of 0.36 plus 0.18 to get the average value. The next analysis, the weighted selected path, considers only the selected paths multiplied by the analyzed demand and the path value. It gives the sum for selected paths only, so P1 and path 1, path 3 in this example. So it gives the sum of the proportional weighted path value multiplied by the analyzed demand assigned to the path. So here we would get, here we are, multiplied by the analyzed demand. In the end, what we get is the total passenger kilometer for the selected vehicles. And in our example, the selected vehicles are the trips that are using paths at least 10 kilometers long. For the last analysis, analyzed demand on selected path, we consider only the selected paths multiplied by the analyzed demand. You can see that we don't have the path value anymore. So the calculation is the sum of the proportions on selected path, so P1 plus P3, multiplied by the analyzed demand. In the end here, we have 54. This results to the demand that is using the selected paths. So for example, we can compute the total number of vehicles which travel more than 10 kilometers. Let's learn how these path analysis can be applied for distance analysis. On a simple network, where we have three paths, so top one, middle one, bottom one, where we know the link times, so after the user equilibrium is found, we know the link length in kilometers. We know that because we have found the equilibrium, the average time on each path is equal, and it's 25.46 minutes. We also know the volumes, 36, 46, and 80. We want to compute the volumes on paths longer than 10 kilometers. So we need to identify, we need to use the analysis that lets us only take the selected path and that uses the analyzed demand and that does not use the path attribute value. So this is the analysis analyzed demand on selected path. And if we apply it, we end up with a total of 54 trips on paths longer than 10 kilometers. Now we will run the same analysis, but on our demonstration project. Before running any analysis, we will want to create the attributes and the matrices to hold the result of the analysis. So we will create a first matrix to contain the average length of the paths. We will create a second matrix called dem10, which will contain the demand on selected path longer than 10 kilometers. We will also create two extra attributes, one for the length at LV10 and one for the turn movement at PV10. If your modeler is not yet open, I invite you to open your modeler and to use the create extra attribute tool. Create extra attribute to create the two result attributes we need. So the first one is a link extra attribute called LV10, link volumes on paths longer than 10K. Click on the run button. And the second one is the turn extra attribute, PV10, turn volumes on paths longer than 10K. So right now I'm working on scenario 3010, practice 4, but you can also work on a fresh copy of scenario 3000. And we also need matrices. So we find the tool create matrix. We are creating the first full matrix with the name average, AVG. The average travel distance, and the second one named M10, demand using paths longer than 10 kilometers. Once we have accomplished that, we can go to the next step, which is running the solar traffic assignment, but this time with analysis to compute the average distance and the total and the demand on paths longer than 10 kilometers. So we open the solar traffic assignment tool, and we already know how to configure it. So I will load up one of the existing specification, the solar traffic assignment.ems, so that I don't have to manually reset all of my inputs. And I will go straight to the section per class analysis. We want to run a first analysis to compute the average distance. So the average distance, we will use the path analysis. So click the box add an analysis. for class 0 because we only have one class. And the link component will be length because we want to compute the average path length. No turn component, there is no distance on turning movements, and the operator will be the summation. The lower value will be 10 kilometers, and the upper value will be 999 for the selection threshold. Then we need to select one of the 4 options here. So if you remember what we have seen a few slides ago, we want our path value, so it's one of the 3 options at the top, multiplied by, so we want to consider all paths to compute the average distance. So this is the first option. Consider all paths and include the path value. The distance will be saved, the result will be saved in the matrix average, which we just created. And this is a first analysis. We need a second analysis to get the demand on paths longer than 10 kilometers. So at the bottom, I can add a second analysis, a second path analysis. The selection is the same because I need to compute paths with a total path value longer than 10 kilometers. So I'm adding the length for every link along the path from 10 kilometers to infinity. But this time, I don't want to use the path value. I only want the demand, so the analyzed demand on the selected path. So I check the box for analyzed demand on selected path. The analyzed demand, if I don't select it myself, we will use the same matrix as was used for the traffic class here. So there are times where you want to use a different matrices. So for instance, if you are assigning trucks, maybe your trucks have a passenger car equivalent value of 2.5. So every truck takes 2.5 the space of a car. My traffic class is a demand matrix in PCE, in passenger car equivalent. But when I want to analyze the number of trucks doing each path, I will want to use the matrix of vehicles, not the matrix of passenger car equivalent. So I can do an analysis on a different matrix here. In our case, we don't want to do that. We will just continue and save the result in DEM10 for the selected demand, in LV10 for the link volume, and on PV10 for the selected turn volume. The stopping criteria does not change, and when we are ready, we can click on the Run button. And I just realized I made a small mistake. So we did an analysis and computed the average distance for each OD pair, but we set up a threshold from 10 kilometers to infinity, meaning that we have computed the average distance for OD pairs where there is at least one path longer than 10 kilometers. This is an analysis that doesn't really make sense. Well, it doesn't really make sense to exclude other OD pairs from the analysis. So we'll rerun our assignment and change the path analysis. Remove here, I had 10 and 9 and 9. So I will remove the selection threshold for the first analysis where we are computing the average distance. And once I've removed the selection threshold, all OD pairs will be selected. After rerunning the assignment, as usual, you want to make sure that by looking at the logbook that the assignment was stopped on your convergence criteria. And then you want to go back in the desktop, refresh the data that you see in the desktop, and find the worksheet volumes on links and terms. It will be in general, in results analysis, traffic, volumes on links and terms. I prefer to add some contextual information, either a base map, or let's add the buildings.eml. So this is a shapefile that I've prepared to look nicer. Looking at our linked layer controls, currently we are showing volume, but we have just computed a new extra attribute, LV10, to store the demand on paths longer than 10 kilometers. So I will display at LV10. So we see what would be interesting to see actually as well is both at LV10 and the rest of the volume. So I will have volume minus at LV10 minus at LV10, comma at LV10. So the bandwidth, the total bandwidth is the sum of long distance strip and short distance strip. And we can compare. So they are, without a lot of surprises, on the main arterials, we can see that there is a considerable share of long distance strip. And when we move in closer and look at local streets, there are fewer long distance strips and more short distance strips. Okay, so this was the first way to look at our results. The second demonstration is by using the zone values from aggregation worksheet, where we display the demand on paths longer than 10 kilometers. So let's find this worksheet. So it's in matrices, zone values from aggregation. And as usual, I will include some media to make it look nicer. By the way, we will have a small video at some point as well, which shows how to have always the preferred background, but always displayed by default so that you don't have to add it every time. So there we are. We go in the matrix layer and find the ODPR value to be MFGUM10. We are now showing an histogram. In orange are the origins, in red the destination. It's already pretty clear that there are some locations where there is more demand for long distance trip or attraction for long distance trips. But I can make it even easier to see by filtering the symbols for the zones where the demand is not high enough. So right now we are showing all of them as long as they are greater than 0. I will display only the origin and destinations if they are greater than 500. So here, first filter, second filter, and we have a pretty clear view of generators of long distance trips and attractor of long distance trips. Well, a clear view of the bigger generators. We notice that the long distance trips are mostly going towards the universities and the airports, which are not at the city center. And there are not so many long distance trips going to the city centers, meaning that the long trips going to the central business district are not necessarily made by private car, maybe by using transit. For our next demonstration, we will look at the distribution of distances weighted by the demand. So we will use the matrix histogram worksheet, which we find in the Project Explorer under worksheets and tables, matrices. Matrix histogram, there it is. The layer controls lets us set the X value to MFAVG for average, which is what we just computed. And the Y value, the weight value, would be MFAUDS, so the demand, the total. As usual, we can control the binning by playing with the by playing with the X range, so 0 to 35 by jumps by bins of 5 kilometers. I will display the numeric value. And move to the title and descriptions here. Set the X axis title along the X axis. The caption will be trip length distribution. For the X description, we will leave it as it is. For the frequencies, we will change it to number of trips. And we now have a nice distribution. If we want some space here for the last numbers to show up, we could play here with the Y range, for instance, so that would be one way. And finally, we want to look at the average distance of trips going downtown. We will use a matrix table to display the odd pairs going to the city center. I invite you to go back to the desktop and open a matrix table. So from create new table, matrix table. First, we want to display the average distance. So the odd value to display will be MF AVG. And right away, we can see that it is displaying values with a lot of decimals. So we would like to add this to just one decimal. And we can do that if you look at the documentation by using the function string mfavg, then a comma, and then we can specify the number of decimals we want to see. So here it will be 1. And as long as we are converting this numerical value mfavg to a string, we will add the units as well. So plus double quote to say that we are adding a string, space kilometer double quote. So now my table is showing the value 0.0 space kilometer. So this is for the average distance. We would also like to show the travel time. The travel time is in matrix MF AUTSK, so that's for the scenario with the Kildonan bridge. And similarly, it shows with many decimals, and we would like to be able to reduce the number of decimals to 0, so just minutes, and to also have the units. So we'll again use the function string mf_utsk, comma 0. We don't want any decimals, plus double quote min for minutes. And now with a table where each odd pair is populated with two values, the average distance and the travel time, the travel time to go from origin to destination. We also wanted to only look at the odd pairs going from outside to inside the CBD. So it means that the origins, we should filter the origin so that the district of origin is not equal to 0. So GA is strictly greater than 0, but the destination GA equals 0. And you can see that as I'm filtering, some rows and columns are removed because they don't belong to the partition, to the CBD for their destination, or to not the CBD for the origin. We would also like to style the table here to highlight in gray long distance trips. So we need to display the style of the table. And to do that, we can go under, I believe it is option, show style specification. And by displaying the style, by clicking on the style here, we will set a style with two sets of filling pen and text. So how do we do that? Either we preload one or we do a right click on the style that already exists here and we duplicate it. For the style at index 1, I will make the filling light gray. So I'm selecting light gray there. Great. So now we have whatever we write in the expression here will yield an index, 0 or 1. And so if the index is 0, we use the first style in white. And if the index is 1, we use the second style in light gray. So I need to write an index here where that allows me to discriminate between the short distance strips and the long distance strips. So the OD pair where the average is greater or lower than 10 kilometers. So MFAVG greater than 10 kilometers. Once I've done that, I can now scroll through my table and identify very easily in gray the cells where the average distance for the OD pair is more than 10 kilometers, 10.5, 13.6. And the rest is basically shorter distance trips. We can also use path analysis in Solar to run select link type of analysis. Let's see how we do it. We still have the same network with the same network results, so travel times here, an average travel time at equilibrium of 25 minutes. But instead of working with the link length, our link attribute will be a select link indicator. We are going to create an extra attribute which we will use as a flag. So its value will be 0 everywhere, and it will be 1 for the links we want to select. We also have the auto volumes as the result of the assignment. The result that we are looking for is to extract the demand on the selected path, so the demand that is going on the path below, so 18, and so the result of our analysis should be 18. We will use the analysis demand on path using select link. We need to set up our path analysis by creating an extra attribute or by using a user attribute, which is set to 0 everywhere except for the link or links which we want to select. The path operator will be the maximum operator, and we will set a threshold of 1. So we select every path where the value goes between 1 and 1. In the example below, we have two different paths, where the first path, we have a value of 0 for the first link, maximum 0, so the result is 0. 0 maximum 1, the result is 1. 1 maximum 0, the result is still 1. So the path attribute value is 1, and we are selecting this path. For the second path displayed, we have 0 max 0 equals 0, max 0 equals 0, max 0 equals 0. So the path attribute value is 0, and the path is not selected. We will store in the OD value the analyzed demand on selected path. Select link analysis allows us to help answer a lot of different types of questions. One, for the sake of the example, we will take one, which is we are building a new facility and we would like to know who is benefiting from it. And without doing any study, it's pretty easy to give a first answer. The locals will benefit. So people living around the new facility will benefit from it because it will make it easier for them, shorter to reach their destination. But we will use the path analysis on selected link to extract the link volumes and time volumes and to extract the demand that benefits from the new infrastructure. For this example, we will work on a copy of the scenario 2000, and we will create extra attributes. So the first one is select link, so a select link indicator. Then two extra attributes, one for LV-BRI, so the link extra attribute to contain the link volume using the Kildonan bridge, and PV-BRI, the turn volume using the Kildonan bridge will be stored in this extra attribute. We will also create a a new full matrix called demkill for demand on the Kildon bridge. I invite you to use the create extra attribute tool. Go and create a new link attribute called cell lk. So select link, selection link flag. The default value is 0, and we will set it up to 1 for the link we are interested in. Then we will have LV bridge, link volume using the bridge. Oh, I'm making a mistake here. Just a reminder, we want to work on scenario 2000. So we will create on a fresh copy of scenario 2000. So we'll open the copy scenario tool, select the scenario 2000, copy to 2001, set the new scenario as the primary scenario, click on run. And now I need to recreate the extra attribute I was creating. So I need the link LV bridge. It already exists. I will check the box overwrite in case it already exists. This way I'm sure it is reinitialized to 0. Okay. I will also recreate the select link feature flag, the select link flag, selected links. I will create the turn extra attribute PV bridge, turn volumes using on path using the bridge. I also need to create a new matrix to store the demand using the bridge. It's a full matrix. It will be called demkill for demkildon bridge. Demand using the Kildon bridge. And we click on run. We need to use the network calculator to set the select link attribute. We can do this from the network calculator, or we can do this from the network editor. So from the network calculator, we want to set a value of 1 in the extra attribute cell link, select link, not for all of the links, only for the links 177 to 10,081 and the link 1081 to 177. And when we are okay, we click on the run button. Summary statistics tell us that we have selected nothing. So I made a mistake in the way I wrote my selection, link selection. It's actually a very simple mistake. I said link going from 177 to 1081, and here I use the condition and. So a link cannot be one direction and the reverse. It can be or, but not both at the same time. I will click on run now after correcting my selection. Now my statistics tells me that we have evaluated the expression on 2 links. So we have retained 2 links in our selection. We have made modifications to them and set them to 1. Of course, I want to take a look quickly in the logbook in the desktop and verify what we have done. So back to the general worksheet, links, the link bar value, I will set it to cell link just to see what is the link, what are the links I have just set. So I've set the link which are constituting the Kildon bridge. I could have done it through the network editor, but This way I did not need to close the modeler. Back in the modeler, I now need to run my solar traffic assignment with a different analysis where we select only the paths going through the link. So we have seen that we will use the link component select link. We will use the max operator with a selection threshold going from 1 to 1. Back to my solar traffic assignment. I will go in per class analysis. I will remove the analysis that I had previously by clicking on the small button here and add a new one. So this time, instead of using the length as the link component, we will use add select link. The operator will be maximum. The lower value will be 1 and the upper value will be 1. We also saw that we want to use the analysis analyze demand on selected path, meaning that we only retain the selected path and we multiply by the analyzed demand, but we do not account for the path value. We also need to store the results of the analysis in the matrix that we have created, EMME, in the link extra attribute and the return extra attribute that we have created. So OD values will be dem kill. Link will be LVBRI and PVBRI for the terms. Once I'm ready to run the assignment with the new analysis, I can click on the run button. And as usual, we want to look at the results. So here on the volumes and links and terms worksheet, which is conveniently already opened from our previous analysis. So back in the desktop, I refresh the data, go on volumes and links and terms, and this time I will show at LVBRI. There we are. We are now seeing a bandwidth plot of volumes, and you can see that as we are getting closer to the bridge, the bandwidth are going thicker and thicker because all of the small demand trickling from the whole network toward the selected link are aggregating along the links, along the path. So it's a pretty nice visualization here that we can repeat for any link we want or any combination of links we want. We also want to look at the demand matrix, so the demand using the bridge. And for this, we have produced, so first we have the zone values from aggregation worksheet, which will help us. And we have produced a new matrix, MF DEMKIL, containing the demand going through the bridge. So the zone values this time, instead of being MF DEM10, will be MF DEMKIL. MF DEMKIL, there we are. We need to remove the filters we had for the origin zones and for the destination zones. And if needed, might be a nice thing to do to recompute, to auto-scale the histogram size. And this way, we are seeing that there's actually quite a strong demand to go from this, I guess, the east shore to the left shore. It's not surprising for the AM peak because the east shore workers need to go in the city center, which is on the west shore. So they are taking the bridge to go to the city center and go about their business. So now we can go back to our initial questions, which was who benefits from the new facility. Now, first answer was, well, the locals will benefit from it because they can just have a better accessibility to everywhere in the city. But now we have a second answer, which is there are general benefits. We have seen that it's not only people local to the bridge that will use the bridge. So there are benefits to more than just a couple blocks around the new bridge. So to understand fully the winners and losers of this new facility, we can do scenario comparisons of the assignment results. So we can compare travel time differences and flow pattern differences. By comparing the travel times, so by basically computing the difference between the matrix containing the time resulting from running an assignment on the scenario without the bridge, so the difference with the time from the scenario with the bridge, that will give us a new matrix, and the values are either positive or negative. So if it's positive, it means that the time with the bridge was longer than the time without the bridge. So I lost it, right? I'm actually suffering from the new bridge. I'm taking more time to reach my destination, probably because there is new traffic on my road. So now there is congestion where there wasn't before. And the opposite. So for everyone where the value of this expression is below 0, it means that the OD pair is gaining. They are winning. There are shorter travel times, better accessibility to their destination. Of course, we want to be reasonable. So if there are small differences, we should exclude them from the analysis. First, because results are not perfect. Remember, we're working with zones. So we are already doing a spatial approximation, and we are working with the assumption that everyone is a rational human being, knowing everything. So not all of our hypotheses are completely correct with the actual world. So we want to exclude small differences. And we can use the matrix histogram worksheet to plot the difference, to plot the distribution of differences, and to see who is gaining, who is losing. So I invite you to open the matrix histogram worksheet, if it's not already open for you. And well, actually, I'm going to open a new one because this one I had parameterized it, given it a title. So I opened a new matrix histogram worksheet. The x value here should be the delta between the travel times, the matrix containing travel times with the Kildonan bridge, which is MF6, minus the matrix containing travel time for the reference scenario, which is MF4. I don't want the x value to be just 1. I want to weight by the demand, and the demand is MF1. So the travel survey is MF1. Because we have said everything, because we have said that every value below 0 is positive, meaning we gain time, we would like the left-hand side, so here the distribution is centered on 0. We would like everything below 0 to be in green and everything above 0 to be in red. So we want to change the style as well. Click on the bars here, load up a style with progressions. Actually, not progressions. I think discrete value, 12 classes is good enough. We have red, we have green. I can remove, so I'm selecting all of the styles I don't want, do a right click, delete selected items. Okay, so I have red, I have green, and my expression will be, what will be my expression here? So if x is greater than 0, let's see what we have. Apply, actually greater or equal than 0. So we have the green on the right and the red on the left. We wanted the opposite. I can either invert my sign here, or I can drag and drop the styles, invert the style. So there we are. Click on OK. everyone on the left-hand side is gaining, everyone on the right-hand side is losing. So you can expect, especially for the one on the lower end of the distribution, you can expect them to not be happy about the new bridge and to complain about it. Maybe it's worth investing a little bit into education or into a special kind of way to compensate these people. I will go now in statistics and show the average and the standard deviation. Then go in the title and description and play with the title here. We want to see the caption, the weighted average. There we are. So right now we have matrix histogram, weighted average minus 0.12. The caption is what is displayed here as the worksheet name, so we'll change that. Travel time difference with Kildonan bridge. Hit enter, and now the caption has been updated here. We also want, as always, we want to set the title along the x-axis so that it makes a little bit more sense. And probably change the x description as well to difference in minutes. It makes more sense for someone reading my graph, my histogram. The frequency here represents the number of trips. So I will change the y description as well to number of trips. And this is a fairly good histogram. I could save the image by going to File and save as PDF, save as SVG, save as image, and include this image in the report. For myself, I will only save the worksheet and save it inside the training subdirectory. If it would also be interesting to be able to analyze every OD pair with a big travel time difference. So what we will do is we will create a new matrix called time difference, and we will run a matrix calculation to store the difference between the times in the scenario of the bridge minus the times on the scenario without the bridge, and we will store the result in time difference. So let's do that. Go back in your modeler, find your create matrix tool. It's a full matrix that we are creating. The matrix name is time diff. The description will be time difference with, without the bridge. The default value is 0, and we run this matrix creation. MF8 has been created. We now need the matrix calculator. The matrix calculator, the expression will be MF AUTSK, so the travel time, the auto travel time for the scenario, the Kildonan bridge, minus MF AUTSB, travel time on the base scenario. The result is stored in time diff matrix, no constraint, no aggregation, as many processors as I want, and run this tool. So now we have a new matrix. The minimum value is -6, the maximum value is 2, and I can explore these matrix values either directly here in the desktop, or if I want to have a list of OT pairs to investigate as a text file, let's look for the tool export matrices. So we have the tool export matrices. Let's see the slide, the corresponding slide. We will export matrices with the biggest differences, right? So we will export the matrix time difference, and we will exclude all of the OD pairs where the value is between -2 and 2. So we only want big time differences. We find the tool export matrices. We are exporting the matrix time diff, and we are applying a constraint by value. We want the time diff, so the value of time diff must be excluded from the slice -2 to 2 minutes. The result will be stored in a new file, which I will name timediff extreme values, and it will be stored in the project database. It could be anywhere else. Let's do this. Maybe also give it a .text extension. The field separator will be the comma, and we will use format values compatible with EMME transaction. We'll skip the zeros, but this doesn't really matter because we have excluded the -2 to 2 range. And here we are running the tool. At the end of the tool run, we have a message telling us that the export was successful. We have access to a link to the file, so we can either click on it directly and it will open the text file, or you could just follow the path. So there we are. We now have a list of origin, destination, and the time value difference. And this list only includes the bigger differences. So everything that's negative is actually a good thing. People are taking less time to reach their destination, and everything that's positive is not a good outcome for our citizens. We now have a practice about analyzing paths. Be sure to come back to the video after your practice, as we will learn more about the different types of assignments that are available. So the PTOL, the path-based assignments, everything we didn't talk yet about, we will see after the practice. I encourage you to put the video on pause and to open your booklet and do the practice by yourself. And then you can come back to the video to see first the correction and second the conclusion. In this practice, we would like to analyze how people are using the highway network. We will try to get the link volumes and the turn volumes for the path using the highway network. And we will get the demand matrix where they are using the highway networks, as well as the average distance traveled on the highway network. We have seen earlier that paths using a particular facility can be analyzed by performing a select link analysis. We will first need to tag the links which are part of the highway, and then run the analysis, run the solar traffic assignment with path analysis set up and configured correctly. In the first section of the practice, we prepare the attributes and matrices to hold the result values and to hold the selection flag. In the second section, we configure the assignment, including the path analysis that we need. And in the last section, we look at the results. So let's start by preparing our network. We'll first make a fresh copy of scenario 3000. If your modeler is not yet opened, now is the time. Find the tool Copy Scenario and copy the scenario 3000 onto scenario 3011. The new scenario will be practice analyzing paths. Check the box override scenario if there is already one. Set the new scenario as the primary scenario. And we can now start by creating the matrices to all the result values. So we need the tool Create Matrix. Oops. And we need to create a first matrix. The name will be Highway Dem, so demand using the highway. And we will check the box to ensure unique names. We also want a matrix for the average distance on the highway, so it will be AVG dist, average distance of pass using highway is the description, and we can click on the run button. We also need extra attributes to store the results. So we need the tool create extra attributes. The first one will be a link extra attribute. The name will be highway length, so HWLEN, and the description will be contain the length of highway links. So the value will be 0 for all links which are not highways, and it will be the value of the length for links that are highways. We need a second link volume attribute, so it will be LVHWY, so link volume highway. Remember that you can use more characters and you can have more descriptive attribute names. You are not limited to cryptic 6 letters attribute names. Link volumes using highways. We also need the turn attribute. So I'm changing the attribute type PV highway, turn volume using highway. And at this point, all of our attributes and matrices are filled with zeros, and that's okay. But we do need to change the values inside the highway length attributes. We need to run a network calculation and set it from 0 to the value of the length of the link if the link is a highway. So we find the network calculator, and we run the expression length. So this is the length of the link, which we store in highway length. And we don't do this for every link. We do this only for links where we are not a highway. So where the attribute highway is different from 0. So not at highway equals 0. If you want to know which links are highway links, you can go to the general worksheet in your desktop and you can apply a filter. So on the link layer control, set highway, well, you can set different from 0 or just highway. And you can see here that only the links where the highway flag is not 0 are displayed. We see the highways coming in the city center and the highways around. Back in our modeler, we will change our link selector to not at highway equal 0. And we can run. After running this calculation, we verify in the summary here, we have changed 262 link values. And in total, there is around 300 kilometers of highway length. We have now prepared our network, and we can move on to section 2, running the assignment. So in the practice, you are asked to use the SOLA traffic assignment, and you are asked to reload the SOLA traffic assignment specification from a specification file, and the one you're asked to use is called SOLA traffic assignment.ems. It automatically populates the GUI, and we see that it's using the car network with MF1 as the demand matrix, and we just need to configure per class analysis. The first analysis is to extract the demand and volume using the highway network. So we'll add a path analysis where the link component is at highway length, the attribute that we have prepared. The turn component is 0. The operator will be the summation, and the selection threshold will be from 1 to 99999. So if I'm using the highway for at least 1 kilometer or more, so that means that if I use the highway for less than a kilometer, I will not be selected. But that's okay. We want 1 kilometer or more. We then now need to select the analyzed demand on selected path. because we want the volumes using the highway. So we want only to consider the path that was selected, multiplied by the analyzed demand. And we don't care so much for this first analysis about the path value. So we check that box. We use the same demand as the demand that we have assigned in traffic classes. The OD value will be stored in highway dem. The link volumes will be stored in link volume highway, and the turn volume in PV highway. That is our first analysis. We need a second analysis to include the average distance traveled on highway networks. So I'm adding a second analysis. And similarly, I will use the highway length as the link component, the plus operator, the summation operator. We don't need a lower or upper threshold. Anyway, because we are, so yeah, we do not need a selection threshold because we are computing the average distance traveled on highways. That means we need to include the paths which are not using the highway. Then we will use the path to the aggregation. We'll use the path option where we consider all paths. We don't consider the analyzed demand, and we do consider the path value. The analyzed demand we don't touch. The result will be saved in the matrix, in the result matrix we have created, AVG highway, average AVG dist. There we are. We can take a look at the stopping criteria, but there is no need to change it, and run the tool. Once the assignment has completed, it's always a good practice to open the logbook and verify that we have stopped on the relative gap or on the gap measure that is the one we decided to use as a criteria of convergence. So let's look at our relative gap rather than our best relative gap. Probably we could have gone a few more iterations to reach equilibrium, but good enough for the practice. At this point, we have modified the SOLA traffic assignment specification, the original one. So we will save the current modifications to a new file, and we'll call this new file SOLA traffic assignment with highway analysis. So later, if we need to rerun the analysis, we can just reload the file. The only thing that remains is to open the desktop and look at the results. So for instance, in the link volumes and on the volumes on links and terms worksheet, which you can find in general, results analysis, traffic volumes on links and terms. Currently showing value, always add some contextual information because it is nicer. There we are. So the links is currently showing value. We would like to see the volumes that we have just generated. So it's LV highway. So these are volumes for all paths using the highway at some point in their path. And I will add a comma, value minus LV highway to see the volumes associated with paths which are not using the highway. And so the sum of both makes up for 100% of the traffic. And as expected, on links which are highway links, the 100% of the traffic is using the highway, and then we see places where there's more of a mix between local traffic and traffic which is destined to use the highway. We would like also to look at our matrix data. So we'll create a OD pair table with the highway demand matrix and with the average distance matrix. The decimals will be set to 2. There we are. And from here, I will add the some summary statistics. So for the highway demand matrix, we will add the sum, the max. There we are. And for the average distance traveled, we will add, nothing for now. But what we see here is that in total, there is above 22,000 trips which are using the highway at some point for more than 1 kilometer. There is one OD pair with 158 trips using the highway. If we want to identify it, for instance, I could use the filter here. I could write MF highway dem greater than 156, for instance. And this gives me the OD pair from origin 94 to destination 103. This is the highest demand to use the highway. I will remove the filter. Let's add to the average distance column the properties of the maximum and the average. And this gives us a maximum of 54 kilometers on the highway and 5.25 in average on the highway. But here there is a small caveat. This is for all rows, including for OD pairs where there is no demand. So I will apply a filter. Highway demand greater than 0, that now gives me the maximum distance where there is actually someone trying to do this path, so driving more than 47 kilometers on the highway, and the average distance traveled on the highway now is 5.06. It is to be noted here that this is the average across all OD pairs. If we want a weighted average by the demand, we would have to add an extra step where we compute the average distance multiplied by the demand, and then we divide by the total demand. This concludes the practice, and we can go back to our slides. We have only a few remaining slides to open up a little bit to other ways of running assignments. The assignment we have been working with so far, the solar traffic assignment, belongs to the family of static models. The delays on links and turns are calculated as a function, which usually is based on the link capacity, the traffic volumes, the free flow speed, or other relevant information. And the delay on one link is not dependent on surrounding links. We don't model Q-spillback or other dynamic phenomena. To represent these other dynamic phenomena, such as weaving, Q-spillback, if we want to have lane-based results or to understand the vehicle dynamics with stop and goes, with cars trying to overpass each other, we need to look into simulation models. And having individual vehicles represented explicitly will also allow us, in addition to everything I've already mentioned, to represent, to model the signal timings. So if we have traffic lights and we would like to have a green wave, for example, we should be working with simulation models. If you are interested in representing dynamic phenomenon, you should contact us to learn more about Dynamic. Dynamic is a software which combines OD-based demand matrices with a vehicle-based traffic simulation. It implements what is called a dynamic traffic assignment, which is an equilibrium model with simulated vehicles and signals, which lets you represent the details of traffic. And it lets you do this at the scale of the city and it contains a lot of nice features to help you along with everything from network generation and details generation to calibration. In M, there are other traffic assignment tools that you can use. We have been learning a lot about the Solar traffic assignment, but there is also the standard traffic assignment, which was the first assignment available in M. It was based on the user optimal equilibrium linear approximation of Franken-Wolf. Its specification is very similar to the one of Solar, but it has a slower convergence. So we actively recommend that you do not use the standard traffic assignment. Today, the Solar traffic assignment is definitely as a faster convergence, and it allows you to reach a better equilibrium as well. We left the standard traffic assignment because we want to ensure forward compatibility, backward compatibility for users who have a model based on it. But if your model is based on the standard traffic assignment, we do recommend that you move, and it's very easy, that you move to use the Solar traffic assignment. The path-based traffic assignment and the associated analysis is a fast converging user optimal equilibrium based on the projected gradient method. It has a good performance and a good convergence, and there is no way to know when we compare path-based traffic assignment and the Solar traffic assignment. There is no way to know which one will be the fastest. It will depend on the network and on the convergence criteria. The paths are saved to disk and analysis are done afterward. Because we save paths to disk, it also offers a warm start feature, which can be used to speed up assignment by reusing class paths information from a previous assignment. Also note that in case you are working with a multi-class problems, so there are more than one class in your assignment, the path-based assignment will have total links and turn flows as a unique solution under the assumption of the user equilibrium has been found. However, the breakdown into class flows is not unique. In comparison, the Solar traffic assignment exhibits the property called proportionality, which is defined as the proportions of flow on alternative route segments with equal costs are the same for all drivers, regardless of their class, origin, or destination. So, as a general rule of thumb, for any reasonably well-converged Solar traffic assignment, the uniqueness of path and class link flows in most travel demand forecasting application is not a concern. However, the proportionality property does not hold for the path-based traffic assignment, which typically produces a smaller path set at equilibrium. That also means that related analysis using paths may require care in interpretation, especially for the subarea demand at gates, which may appear lumpy after a traversal analysis, even though the subarea demand is correctly reproducing the total link flow. This is one reason we do not encourage traversal analysis with the path-based traffic assignments. The Python traffic assignment is based on large part on the fast converging traffic assignment. It has additional features to allow for easier modeling of toll facilities and represent advanced tolling schemes such as distance-based toll with capping or ramp-to-ramp tolls. The stochastic traffic assignment implements a stochastic user equilibrium assignment. It computes the average of several separate multi-class equilibrium assignments where the link costs are perturbed by using one from a choice of 3 distribution functions. Link volumes are obtained by averaging the results of a number of separate multi-class equilibrium assignments, each computed with a different set of random terms. This assignment is used for applications where multipath effect is not due solely to congestion or where the user equilibrium assignments may result in an all or nothing assignment on uncongested network. So for instance, think of a rural, regional, or national application. We already used the solar traffic assignment once, the continued traffic assignment once, which is useful to continue an existing traffic assignment for more iterations to ensure that we have reached user equilibrium. And so this tool will work to continue solar traffic assignments or PTOL or path-based traffic assignments. Then we have the space-time traffic assignment. It provides a new traffic assignment for time-dependent multi-period network loading with the convenience of existing network topology and delay functions. Demand matrices may be optionally profiled over time, and the network is loaded differently across time periods as flow progresses through the network. This method is especially recommended for statewide, national, or long-distance freight models in which longer trips should not simultaneously load all time periods at once. The analysis capabilities and results are similar to those in other traffic assignment methods, but they are additionally specified by time period. If you want to learn more about about all these assignment tools, you can read the EMME modular manual, or you can follow the traffic application course. Thank you for